Sharing my screen. So hi everyone, welcome to Multimodal Weekly. This is a virtual webinar series hosted by Labs, which is a startup. We focus on building foundation models for video understanding. So we've been meeting on a weekly basis, pretty much every Friday over the past year and a half or so. Here are some of the topics that we would like to cover on a weekly basis. We're a big fan of researchers, so I find relevant researchers who are working at the intersection of multimodal AI, video understanding, foundation models to come present their work, at a webinar for the community to learn about. Occasionally, we have speakers from the industry talk about application, right, of multimodal in different verticals. Since our company focuses a bit more on video, we also have folks working in the industry who build video projects and share that with the community. And we also have internal team member come talk about how to use our platform and API. I've been focusing a lot on the research side of things recently. You can see here the list of the speaker from some of the recent sessions. Folks working on a variety of domains from video segmentation to video question answering, speech recognition, benchmarking multimodal models, working on video retrieval, etc. So for today's session, really excited to have three speakers, researchers working at different aspects of video and computer vision, multimodal AI. So we actually get started with Siyuan Li, who will be the first speaker. He will talk about his recent project called Matching Anything by Segmenting Anything. The title is called Tracking Everything, but it's really cool work that looking at tracking level objects within video frames. The second speaker is going to be Jaewon Son, who will talk about his work CSTA, convolutional neural network spatial temporal attention for video summarization. Obviously, a very interesting topic for 12 apps as we also build solution for video summarization, question answer. And finally, Jinwoo Ahn, who will talk about compositional video understanding with spatiotemporal structure-based transformer. Right. Obviously, video understanding a very relevant topic for us. So yeah, excited to hear more about the methodology that you build for this work. Quick logistic note for the attendees: feel free to send your question in Zoom chat, and then I submit them to the speaker. And then a session is about 15 minutes, and then we'll have a short 5-minute Q&A after the speaker finish. So with that, I'll stop sharing my screen, and see you. You want to go ahead and get started?
Okay, cool. So can you all see my screen?
Yep. It's looking good. I see it.
Okay. Hello everyone. I'm Siyuan Li. I'm from Computer Vision Lab at ETH Zurich, and I'm very happy to be here to share our recent work, matching anything by segmenting anything at CVPR this year. So first, a little bit of motivation of our work. So as we know, like computer vision or AI, today people want the model to deal with lots of things. Like you need to generalize the model to, for example, for tracking, to generalize the model to different type of objects. Also, hopefully, any domain that the tracker can work. And this is very crucial for the success of multi-view tracking, and it will benefit many downstream tasks such as AR, robotics, like drone and autonomous driving cars. But the current problem is like, I think if we think this computer vision task, nearly every computer vision task like 3 years ago still focus on very small scale, limited scenarios. That object detectors only detect COCO AT classes. Also like trackers only track like people or cars in this very representative MOT challenging data sets. For example, just one class, which is tracking pedestrians, or KT or other autonomous driving data sets, just tracking pedestrian and cars. So, training on those data sets with those kind of very limited domain kind of hurts the generalization ability of tracking methods. That's we cannot simply develop a model that enable us to tracking anything with such data. So so today I'm going to talk about how to scale up the tracking task in order for us to develop trackers that can track anything. So the scaling up has shown, like, I think, a lot of magic advantages. For example, if you scale up the models for video generation, you can generate like very realistic videos as we have shown by Sora, and they have very interesting like ablation study that actually show that with more compute data and larger network, you can actually generate like far better results. So so that leads to the questions. What is the condition to scale for the tracking task? Usually, like for scaling up, you need massive raw data, and you need reasonable and cheap supervisions. If your ground truth or your supervision are too expensive to annotate or to get, it's very difficult to scaling up. And this is true, and we can see from these examples, LLMs like GPT, they can like use internet level, like massive raw test data, and this video generation model can use all the raw videos on the website. And for our tracking task, we can also access, I think, lots of raw videos and images. So this is a good. And regarding supervisions, I think large language model, their supervision is very cheap. The pre-training stage is just next token prediction, so it's basically self-supervised. And for Sora, and it generates raw videos, and usually one video you only needs one like very detailed text prompt, so also cheap. So, but for tracking, as we all know, it's very expensive to annotate all the mask bounding box. So so if we cannot like annotate all the tracking supervisions manually, how can we scale it up? So we need to think out some other supervision signals, for example, self-supervisions. Also, with self-supervision, we should be able to train with raw images or videos. And the most important ones is that we can get this great generalization ability as a result of scaling up. So let's first revisiting some self-supervision signals of previous methods that this paradigm I think is can like summarize most of the methods. The main idea is you try to augment the single image you have with different kind of pairs, and you try to learn representation, putting like the same augmentations representation closer to each other, different images away from each other, and but this only like you can train with ImageNet images, because that's ImageNet images only like have this object level kind of object-centric image data. And another like self-supervision signal is you try to manning this representation from raw videos. For example, with like previous methods called VFS. The basic idea also have like many variants of this kind of methods is you direct video frames, and you assume this object presents on different video frame, and so if the frames from same videos, you assume their representation should be close, and if the frames from different videos, they should be pushed away. Basically, that's the same idea. Also, it requires like object-centric video data. As I can show you, like they're training with such data sets, which is very clean. And for videos, it's almost one object per frames. But for the real world images is usually very messy. You have multiple objects coexist in these same scenarios, and to do self-supervision with this kind of images is hard because you basically you cannot say that this frame 1 and this frame 3 are the same because all the objects like changes. So here comes our key idea that we want to explore self-supervision signals on those massive enabled images. We do not only want to use like ImageNet kind of very clean images, object-centric images, and we are able to do so by this new segmentation foundation model called SAM. So which SAM can give like very accurate incident level informations that's that is already encoded in the SAM pre-training. So the whole idea of this our model is very, very simple. First, we connect a huge unlabeled images from data sets from diverse domains. And this image usually like also contain multiple objects. And we bootstrap from this large raw image data sets. And then we do a data transformation, geometric transformation. So if you apply this kind of geometric transformation to the raw images, you basically can like trace where is each pixel going. So you have this pixel-wise correspondence when you apply different transformation for the same images. And with this kind of point correspondence, with SAM, it can turn a point into a silhouette, a shape that directly transform this kind of pixel correspondence into incident level correspondence with all the incident shape informations. And those incident correspondence is exactly what we need to learn this instance-wise representation for tracking. So then we utilize those transformed instance correspondence to train a simple appearance model that's trying to push all the instance that's from the same objects closer and push other instance embedding from other instance away. So during training, so this is a simple training pipeline. So we call this a MASA adapter because it can reuse some image foundation models feature. For example, the backbone features can from SAM, can also from any object detectors. And we frozen the feature because we do not want to destroy the detection ability of those image trained models. And then we have a learnable module called MASA adapter, which basically transfer these backbone features in multi-scale and kind of fuse multi-scale informations. And then we add two heads, one detection head, one track head, very lightweight. And we train with multitask learning. First, we distill the object prior by applying detection loss on this dense region proposals generated by SAM. And then we have a track head, which learn how to push the embeddings together if it's from the same object and push the embeddings away if they're from different objects. And once the training is done, and we can directly utilize this learned MASA adapter to do tracking. For example, if you have a detector, you add up on the detector with MASA adapter, train with our ways, and then given images, you predict bounding box with your detector, and also our MASA detector adapter can directly provide you features for each object that you detect on different frames, and you can just use a simple nearest neighbor to match these features to do tracking. And this same can work with SAM. For the SAM you can treat SAM as a proposal generator because last step we learn how to distillation the detection knowledge from SAM. So you can also track all the SAM's mask. And as simple as this, we train with completely unlabeled raw images and out of domain, and we test on this popular like um, open world tracking benchmark, and we show that we is directly like become state of art, like without even seeing any images in this testing benchmark. So I highlight the association score because for the like good understanding, we use the same like detection bounding box just to make it fair, because usually if you have stronger detector, you have stronger tracking results. So we use the same detection bounding box, only test the association ability. And so yeah, same model trained with raw images directly sort out like different benchmark, also for driving benchmarks. And for example, compared to Uninex, which previously is a foundation model trained with lots of videos, we can achieve better association score compared to Uninex. So here's some qualitative results. So even with train with like only raw images, I think it generates quite well to different shapes. Like when you camera angle changes, that's um, and because the model is trained on tens of in very large scale, so you can directly just generalize different classes. So for example, previously we see the millions, the, the boats, now the animals, different kinds of animals. Also generates fake data. This Sora generated videos also works with this crazily like amount of fish. Okay, there's some quality results, and now I want to see some connection with VOS-based methods. Like recent, we also noticed there's SAM2 segmentation, anything in video. So this kind of like current strongest VOS-based approach. So people would say if you use such VOS-based tracker, you can also achieve similar effects that you can track anything, but I will show you some like disadvantages of this VOS-based tracker. So because we with submission of our paper, there's no SAM2, so we test the DIVA, which use XMEM. I think XMEM also in our test in SAM2's paper. So actually, when you densely track like all the objects together, when with new objects coming in and old objects like leave the thing, new objects keep coming in, it's quite a challenge for this like VOS like propagation based method like SAM. It cannot deal with new objects. You have to run detector every time, and once you have multiple objects, it's very bad. For example, for example, you will have propagated the wrong object mask into this scenery because the object already leave the scene, but still encoded in their memories. So so this kind of methods is kind of not very ideal for this multi-object tracking scenario. And we can compare another thing. We run track and segmentation and RVC models. I think it's a little bit stuck. So the video might not play. Okay, I think some issue playing the videos. Okay, I'm a little over time, so I was about to talk about some evaluation, but I think I will skip this part. So but there's one thing I want to talk about, like in open world scenario for tracking, you never get exhaustive annotations to evaluate your data set. For example, you always will have problem that because your data set is not exhaustive annotated, you will have, if you evaluate the traditional metric, you will end up tracker at the left side to get better performance. And so we have this new TETA metric, which is designed by local cluster design. For example, we only like evaluate the results under local cluster assumptions, and it can perfectly deal with incomplete annotations. And also we have more comprehensive analyze results compared to previous metric. So if you are working for multi-class multi-view tracking or open world multi-view tracking, I think TETA metric is definitely the metric you should consider to use. And it has been adopted by many follow-up papers. Though it's quite a new metric, we proposed this metric like 1 or 2 years ago. So okay, that's all of my talk. Thank you.
Awesome. Yeah, thanks a lot, Siyuan. Thanks for going over, uh, I think very impressive qualitative results that you show and at a high level display of the method. Um, since we're running a bit out of time, maybe we can do the question asynchronously. So the audience, if you have any question, you can just put on the chat and then Siyuan would do his best to answer the question. Before we move on to the second speaker, Siyuan, I know since CVPI, you've been publishing quite a good amount of other papers, right? I think you have 2 papers on ECCV this year, then you have something Walker, Slack, Samba. I was taking a look at some of your research work. Would you mind sharing some high-level overview about what are the research work you're working on, and how is that moving with the direction related to video object tracking?
Yeah. So object tracking, I think in the end, because MASA like we train with raw images only, but that's because the video data is too hard to get all those annotations. But in the end, I think we should also move from like to be able to train this long-term tracking ability. We need to use videos, but we don't have the annotations. So first we need to also think of self-supervision signals on videos. That's one thing I'm working on. Another thing is how to model these long-term memories for the trackers. Now all the multi-object tracking papers, I think, still use quite naive memory system design. For example, just a list, a queue to store instance features for every object. But how do we design a learnable memory module that can like learn and adapt objects, remember objects' appearance from different view, different angles, and try to utilize the most effective appearance features in the past to help tracking in the future, and how to design such memories and also robots to occlusions is very challenging, and I think it's also very interesting by many people for multiple tracking. Our work, Samba, also like do some explore about memory design, and our paper worker is trying to do self-supervision on raw videos. So I think all these 2 directions are quite interesting. If they can solve and combine together, I think we can develop next generation like trackers. Yeah.
Awesome. Yeah, thanks, Siyuan. Super excited to hear that, and yeah, excited to see some of the future work that you got. All right, so let's move to the second speaker. So Jaewon, do you want to go ahead, share your screen, and talk about video summarization?
Yes, can you look at my screen?
Yes, I can see it.
Yes. Hi everyone. My name is Jaewon Son from Sungkyunkwan University. I'm really glad to have a presentation for this webinar. Title for today's presentation is CSTA CNN-based spatial temporal attention for video summarization. Our paper was published at CVPR this year. There are two main points in our paper. First, we we consider video data as image data. Second, we utilize CNN as attention. So let's begin. Task of this paper is video summarization. This task aims to train models to summarize long videos the way humans do. We input long videos into models and then train models to pick important frames from the videos. After selecting all key frames, we can create summarized videos using those selected frames. Models need to understand video content to exactly find key frames from the videos. This is the overall workflow for training video summarization models. Models are trained to predict the importance for each frame. First, we input frames into the frozen CNN models to extract frame features. Next, we input frame features into video summarization models to extract video level features. We apply frozen CNN model to each frame and video summarization model to all the frame features. Lastly, we input video features into the classifier to predict score. Each frame has a score between 0 and 1, showing how much important each frame is. The important frame has a high score, and the non-important frame has a low score. For supervised learning, there is a target score for each frame, which is assigned by humans. To focus on key frames better, attention is a commonly used method. And there are two types of attention. The first attention is temporal attention. It considers temporal relations in the video. As you can see, models understand the relationship between two frames by comparing their features. After comparing all pairs of frame features, attention is calculated based on all the relationships in the video. Therefore, this calculated attention is called temporal attention. The second attention is spatial attention. It considers visual relations on the frame. There are important and non-important things on the frame. So models need to focus on important ones to understand videos better. As you can see, models understand the relationship between visual attributes of features by comparing them. By calculating attention based on these relationships, we can emphasize important visual attributes. For precise attention, considering both temporal and spatial attention is necessary. There are papers using spatiotemporal attention, but they required huge costs for better results. Previous works construct an extra model to include spatial attention. For example, the figure on the left is based on object detection model. They input all the frames into object detection models to find meaningful objects on each frame. The figure on the right is based on self-attention model. They input all the frame features into self-attention model to find important visual attributes for each frame feature. They showed that spatial temporal attention performs better than temporal attention. However, processing every frame by additional model is very costly due to the lengthy videos. So the goal of this paper is video summarization models considering spatial temporal attention and efficiency. Our approach is CNN attention. We consider video data as image data and then use CNN for spatial temporal attention and efficiency. As you can see, if we stack all the frame features along the time axis, we can create two-dimensional data. And then we regard these data as image and apply 2D CNN models to that. By applying CNN models, we can calculate spatial temporal attention and reduce costs. There are two motivations for it. First, CNN models learn position information within images. Second, CNN improve efficiency for attention models. The first motivation is that CNN learn position information within images. The figures on the slide are the absolute positions within images, such as the right part, the lower part, or the center part of the image. There are papers already proving that CNN models can understand these positions in the images during training. Based on these studies, we propose that we can utilize this ability by treating video as image. If we use this ability, CNN models can find locations of important part for summarization. Therefore, CNN models can work as attention after learning key locations in the data. The second motivation is that CNN reduce cost for attention models. As you know, attention is very costly when the data size is too large. There are papers using CNN to address these cost issues for attention models. The graph on the left shows that CNN-based VIT requires fewer parameters and performs better. The graph on the right shows another CNN-based VIT demanding less computation and also performs better. Based on these studies, we try to improve efficiency by using CNN because the data size is large in video summarization. This is the overview of our model CSTA, CNN-based spatial temporal attention. 2D CNN creates attention maps by considering frame features as images. We input stacked features into CNN models. During training, CNN models learn to focus on key locations for summarization. Based on the outputs from CNN, we can create spatial temporal attention maps. After merging attention maps with input features, we input them into the classifier to predict scores. From now, I'm going to explain our model's architecture. It must take a long time to explain every little details, so I'm going to explain it briefly. You can see the details from our paper. The first process is embedding process. From frames, it extracts embedded features which are used as input. The second process is prediction process. It predicts scores using mixtures of embedded features and pulled features. First, we create key and value embedding like attention models. And then we input key embedding into attention module to create pulled features. Pulled features are created by the CNN models, so it includes key locations for summarization. These pulled features are mixed with value embedding in the mixing module. After mixing module, classifier predicts scores using these mixed features. This is the process of attention module. It creates pulled features by using 2D CNN models. We use skip connection to train CNN models better. And then we utilize an adaptive pooling layer to handle the various lengths of videos. This is the mixing module process. It combines pulled features and value embedding. Before combining them, we apply softmax along both time and dimension axes. Temporal attention is calculated along the time axis, and spatial attention is calculated along the dimension axis. This is how we can get spatial temporal attention maps from CNN outputs. After merging attention maps with input features, we input them into the classifier to predict scores. So far, I have explained our proposed method. From now, I'm going to show you our experiment. The first experiment aims to prove that CNN can function as attention. We can prove that by observing the video summarization performance. The goal of attention is to find important parts from the data. And similarly, the goal of video summarization is to find key frames from the video. So both methods share the same goal, which is to pinpoint the important parts from the data. So if the model shows good video summarization performance, that model can effectively serve as attention. Based on the insight from the previous slide, we perform experiment to see if CNN models can find important parts from the data. We train CNN models to summarize videos and compare the results with conventional video summarization models. As you can see in the graph, CNN models outperforms the traditional video summarization models. For the SUMMI dataset, CNN models like ResNet, GoogleNet, EfficientNet, and MobileNet achieves better performance than the previous video summarization models. And similarly, for the TVSum dataset, CNN models continue to show better performance, while VOS-net outperforms some CNN models, but most of the CNN models still demonstrate significant performance. This indicates that CNN models are good at understanding key frames from the videos, which means they can function as attention. Based on these results, we construct CSTA based on CNN models as attention. To see the power of CNN models as attention, we compare performance of CSTA with previous research. In the table, rank indicates the average rank based on two evaluation methods. We list all the models according to their overall ranks across both benchmark datasets. As you can see in the table, GoogleNet serves as the baseline model for CSTA, and it already demonstrates comparable performance compared to existing models. Moreover, CSTA ranks the best on the SUMMI dataset and second best on the TVSum dataset. While DMA sum performs better than CSTA on the TVSum dataset, but it shows much poorer performance on the SUMMI dataset. So overall, CSTA achieves the state-of-the-art performance because it leverages the power of CNN as attention, unlike previous research. To evaluate the efficiency, we compare computation cost of CSTA with previous research. We measure MAC during feature extraction step and score prediction step. Feature extraction step is the process of converting frames into features. The score prediction step is the process where video summarization models predict scores. We show MAC values along with the average rank from the previous slide. We also categorize models like multimodal, spatiotemporal attention, and temporal attention models by denoting mark next to each model. As you can see in the table, previous works require a lot of computation or multimodal data to get good results. In contrast, CSTA demand less computation with fewer MAC values. Moreover, CSTA achieves the best performance without needing any extra data from other modalities. This experiment shows that using CNN works well for video summarization because the data size is large. So let me conclude today's presentation. To sum up, even though spatial temporal attention is essential in video summarization, it often requires huge costs. We approach this by regarding video data as an image and applying to the CNN models to that. We also utilize CNN as attention and propose CSTA. Our contributions are as follows. First, this is the first paper to apply 2D CNN models to frame features in video summarization. Second, we introduce CSTA as the efficient spatial-temporal attention model for video summarization. Lastly, CSTA achieves state-of-the-art performance with less computation. So thank you for listening to my presentation. And again, thank you, James, giving me this opportunity. If you have questions, yes, please ask me.
Awesome. Thanks, Jaewon. Really appreciate you spending time walking over the presentation. So yeah, since we only have 50 minutes left, let's take some of the question, asynchronously via Zoom chat. So if you have any question for Jaewon, please put that in the chat. I also post the link to his GitHub code base. So if you're interested in just taking a look, review the architecture, and take a look at how he apply CombiNet. Again, highly recommend taking a look at it. Very, very interesting framework approach, and I think it's very closely, I guess, like aligned with what we are working on to allow, which is that focus on spatial temporal attention when we processing video. With that, I will unmute Jinwoo, and go ahead and share your screen and talk about your work on compositional video understanding.
Okay. All right. So everybody can see my screen?
Yes, I see it.
Okay, great. So hi, also happy to be here. And my name is Jinwoo. I've graduated with a bachelor's degree from Hanyang University, South Korea, and currently working at Korea Telecom. So today I'm going to present my paper, Compositional Video Understanding with Spatiotemporal Structure-Based Transformer. This paper is submitted and accepted in CVPR 2024. So to motivate our work, I want to start with our research question, which is how to understand long videos composed of complex semantic structures. So when presented with videos like on the left, where multiple objects are moving and interacting simultaneously, and questions like those on the right, answering them requires understanding the movements of each object over the time. But like conventional video encoders like VIT or Frozen have been focused on very short-term clips, and they train to get visual representations by sampling each frames and feed them into the CNN or transformer-based architecture, which is not very efficient to understand the underlying semantic structure of the video. So our main problem was to build model which understand the underlying semantic structures of a given video. So we tried to tackle this problem by proposing a compositional video learning algorithm, which learned the multi-granular semantic structures of a video. And we thought understanding a video compositionally means, So we thought understanding a video compositionally means breaking it down into its smallest unit called a semantic unit, and then understanding complex semantics through the combinations of this result. So to do this, we first represent semantic structure by converting the video to a spatiotemporal symbolic graph, and then semantic unit representation is obtained by tokenizing the graph into each node and edges. Then the semantic unit representation is obtained by units are combined to represent more complex semantic actions such as spear slide, before, cylinder rotate that exists in the video. So to show our idea, we've conducted on two tests. One is complex action recognition, which is to predict composite actions with a given video, and and each composite action is composed with two atomic actions and its relationships, and each of these atomic actions is composed with object and its motion. And the other one is compositional generalization test, which is also an action recognition test, but need to predict unseen labels that are comprised of combinations of two or more semantic units, where individual semantic units are seen during the training phase. And actually, there are two types of computational generalization tests. One is swapping the temporal order of the labels, and other one is swapping the object and its motion. So now I want to talk about our compositional learning framework, which is composed with 4 steps. So at the very start, we need to convert each video into spatiotemporal graphs. So to do this, each frames are converted with graph snapshot, which is defined as objects in the videos, and the spatial edge are defined within Euclidean distance between the objects. And finally, by linking the same objects over the time and adding the temporal edges, we converted it into a spatiotemporal graph. So actually, the video is represented as an ordered set of this graph snapshots. So next, in order to encode the spatiotemporal graph, we need to tokenize this graph into semantic units, which we define as 3 token types: node, spatial edge, and the temporal edges. So these semantic units are formulated to input tokens of spatial-temporal graph transformers, which we designed. So each of the input tokens to the graph transformer is consisted of token type identifier, which show which semantic unit element of this token is, and the positional embedding from the graph Laplacian eigenvector, and finally the feature. So through this model, semantic units can be combined and represent complex semantic units, semantics with the self-attention layer. So next, to learn object level action representation, we group the output of spatiotemporal graph transformers, output tokens with object indices in the object-oriented video encoder. And to make these tokens corresponding to each object over time, we apply the causal mask of self-attention to this encoder. So the actual output of this encoder is object-centric, object-specific representations encoded with its temporal movements. So since we need to understand the video in terms of its semantic elements, such as objects, actions, and temporal relationships, we introduced the embedding disentangling model and the composition laws to learn each semantic element using object-level representation. And recently, many people asked us about how this embedding disentangling model and laws is actually defined. So I'm going to talk about this in more detail today. So the goal of this model is to break down object-level representation to each semantic element. To do this, we adopted 3 classifiers of predicting each semantic element, which is just a feed-forward layer. So from the output of object-oriented representation, we first retrieve embedding from the predicted semantic element from the action and the object classifiers. Then we concatenate them to obtain embeddings for each of the ultimate actions. After that, we adopted permutation process to obtain embeddings for the temporal relationships between the atomic actions and trained using the temporal relationship classifier. So the composite loss is just simply the sum of each classifier's loss, and each of these laws is just cross-entropy. So by following our compositional learning framework, we have achieved the state-of-the-art performance in complex action recognition tests. And this result is actually quite remarkable because it's via VAT and frozen as modern transformer-based video encoders, but our model outperformed, although we trained from the scratch. And during the rebuttal phase, we've requested to test on real-world data set, and more longer data set like MoMA LRG. So we conducted experiments on MoMA LRG data set, which is like on the right, but also we got higher performance than the modern video encoder. And finally, the result of compositional generalization test is also interesting. So as I mentioned earlier, compositional generalization test has 2 types of object and motion combination and temporal swapping. But in both cases, like previous models showed a huge performance drop in the test phase, but our model showed relatively very small drop in performance because by encoding video with semantic element unit, it is relatively easy to compose unseen label with same semantic units. And it shows really demonstrating our proposed learning framework. Yeah, so that's all about our paper. And if you need more information, use this QR code to visit our project website and contact us at any time. Thank you for inviting me.
Awesome. Thanks a lot, Jinwoo. Yeah, so we just almost right up on time. About 5 minutes left. Yeah, so I just gonna unmute all the speakers just in case if there are any questions or anything you want to share more for the audience. So put the code of Jinwoo's paper on the chat as well. So if anyone wanna quickly take a look at that literature one more time. You can review it. I think it's a very interesting framework. It's leveraging graph transformer. I haven't seen a lot of like graph transformer, to be honest, when it comes to video. So that novelty is there. Yeah.
Thank you very much.
Yeah. Well, maybe one question from my end is like, what would be the next, if we want to improve the performance of this approach more, how can we go beyond graph transformer? Yeah. What are the additional enhancements?
Yeah, actually, that is a really great question because our model has also limitation. Like, for example, we need to have this kind of annotation at the background of the data set. So we use synthetic videos to get each of the location of the objects to build the spatial temporal graph. So like, I think we can use like track anything model to build this kind of graph after next time. Then it is really like end-to-end training. I think that is gonna be our next
Nice. Yeah.
project.
Perfect. Yes, maybe you can connect with Siyuan on the code base for your MASA and apply that for the data setting.
Have you considered deleting all of your possessions?
Yeah, we will release the next version of MASA soon. So yeah, it will faster some too in terms of tracking the semantic of objects and have good memory system. So yeah, we can connect.
Yeah, probably. That'll be great.
Yeah, just one note on I think for both Jaewon and Jinwoo, I think both of you focus on spatial temporal attention within video, right? A bit from different approach, right? I think for the CSTA paper from Jaewon, I think you looking at the spatial temporal attention, and then on Jinwoo paper, you focus.
Oh, I'm sorry. Can you please?
Yeah, I'm trying to figure out the difference on the two paper on the spatial temporal element.
In the anti-scale repo.
Yeah, the basic difference is we use like graph transformers and the Jaewon used the CNN-based spatial temporal attention. So yeah, that is the biggest difference thing. And since we use graph transformer, we can encode the connectiveness of the relationship between the lower, like the multigranular semantic structures. Yeah, I think that is the most different part.
Yeah, I see. One's leveraging convolutional neural nets, and the other one is graph transform. Right, those are the two basic architecture decisions. There's one question here from Parker on the chat. He said, do you think it could be possible to connect these different encoding methods, whether it's graph or otherwise, with a large language model through some shared projection space? And that seems advantageous in any way. Yeah, so maybe an open question for all of you.
Okay. Oh, so yeah, so actually I'm working like other projects to doing like subspace clustering or using an LLM to mapping into the different projection space. So yeah, I think that extending this paper would be very alike to applying to different LLM, but there must be limitations for like building the spatiotemporal graph or other kind of graph. Yes. But if graph is like given, then extending into the other model like LLM would be great, I think.
Got it. But for Jaewon, do you think you can leverage LLMs as a component in any part of your, video summarization stack?
No, yeah.
Oh, oh, I'm not sure. Uh, oh, well, because I don't know that at all. So yes, it's difficult to answer that.
Or maybe we can use like additional cross-attention layers to LLM using this kind of module, like different kind of thing. I think we can extend it like into cross-attention layer to like plug in these graphical features or like spatial temporal attention, like Jaewon introduced, I think. Yeah.
Okay, yeah, no worries. Awesome. So yeah, I think we just right on time, and yeah. So thanks everyone for making it today. Jinwoo, you wanna stop sharing the screen? I think we're still sharing the screen.
Okay, yeah.
No worries. But yeah, thanks for the speaker preparing the materials. I think really exciting research work across different domain, and yeah, I'm looking forward to future video and multimodal work that come up your respective research program and or even industry. Thanks for the participants for attending, and we run this session on a weekly basis, so you all the content here impactful. Yeah. Stay up to date, enjoy our community, and show up next time as well for future sessions. Thanks everyone, and hope you enjoy and have a good rest of your Friday or the weekend. Cheers.
Aurora. Yeah.